Hello, this is my final project presentation. The PhET simulator I chose to use was the one on charges and fields. I'll show that in a moment after I give a brief explanation. So what is charge? Charge is an electric charge is a property of an object that causes it to be either attracted to or repelled from another object, depending on the other object's charge. And an object can have one of three types of charges, that being positive, negative, or neutral. But the PhET simulator doesn't deal with neutral charges, so we are only concerned with positive or negative charges and how they interact with one another for this project. Two objects of the same charge will repel one another, but two objects with opposing charges will attract one another. So that's where the whole opposites attract adage kind of comes from. And the unit for a charge is a coulomb, but the PhET simulation deals in nanocoulombs, which are 1/1000th the size. So that kind of tells you that it's dealing in like atomic or subatomic particles. That's kind of a hint for that. So that's charge kind of simplified. Moving on to what an electric field is and what voltage is and how they relate. An electric field is a physical object created by the aforementioned charges and transmits charge between the different objects in the field. And the field is a physical thing and exerts force on all the objects within it. Like it's a vector, it has both a direction and a magnitude to it, and that magnitude is determined by the voltage. So the strength of an electric field can be determined through its voltage. And what voltage is basically, you can also call it electric potential difference. It refers to the amount the magnitude of an object's energy can change at any given moment. So kind of how volatile a field is. That's why when people say like danger high voltage, well, that's why high voltage is dangerous, is because like, it can rapidly change in strength and thus electrocute you. And so going into the PhET simulator, we see that we can either add a positive charge, which like I said repels, or a negative charge, which will attract. And an interesting thing is that if you were to place one on top of one another, if I can do it, they cancel out. It creates a neutral charge, so that's something neat. But what we also have is a way to measure voltage, the equipotential. I feel like I said that wrong, but it'll tell you at any given place how many volts are present, negative or positive. Like you can see a very high negative number for this negative particle, and obviously a very high positive number for the positive particle. We also have a ruler tool to measure distances, and that's going to be very important for my experiment. We can toggle on and off the voltage of the different particles, as well as the values present, and we can overlay a grid if need be. And I'm not sure what the purpose of that is, but I guess aesthetic. But going back to my question consisted of two parts. I sought to find out how the voltage of an electric field would react to two opposing charges moving further away from one another. That's the first thing I wanted to do, and the second, building off of that, I wanted to find the mathematical relationship between the two. So I wanted to see whether it was like an positive exponential, negative exponential, inverse, inverse squared, whatever graphically, is that the word? Probably. The relationship is. And my hypothesis for the first part was that it would decrease, but I couldn't make a guess at the relationship because it could have been one of many things. And so the way I set up my experiment, let me refresh this, I would place two opposing charges some distance away. It was 50 centimeters in my trials, but I'm not going to measure it out here because that'd take too long. And I would measure the voltage in the center, which I would also do more exactly with the measuring tool, but I'm not going to do that in here for time's sake. And then for each trial, I would move each particle equal distances away and see how it would affect the number in the center, how it would affect the voltage. And after I graphed this, I can see I said it wrong. I started at 100 centimeters distance between the two and increased all the way to 500. And you can see here the intensity in volts clearly decreases. I also graphed 1 over the distance and 1 over the distance squared for the purposes of finding the nature of the relationship. And so you can see in the basic graph of distance over intensity that there is a stark decrease in intensity over the distance. But what's also noteworthy is that the intensity drops very quickly at the beginning, and then as the distance increases further and further, begins to slow down and decrease less and less quickly. So that made me wonder if it was an inverse relationship between the two quantities. And so I looked further in, and I graphed distance against one. I graphed intensity over 1 over distance and 1 over distance squared. And so after that, I found that one intensity versus 1 over distance was close. It wasn't perfect, but it was more linear than just the basic distance versus intensity. And so that kind of got me set that it was an inverse relationship. And so I went further into graphing it, and I graphed the intensity versus 1 over distance squared, and that did turn out to be a perfect relationship. I have an R-squared value of 1 for my data, so that tells me that the answer to my second part of my hypothesis is that it is an inverse squared relationship between distance and intensity. So that's to say that the potential a field has is directly proportional to the inverse square of the distance between two separate particles.